Hello, everybody. All right, so we are moving on to our second topic in derivatives, and we're going to talk about the derivative as a function. So what we're going to do here is we're going to define and graph the derivative of a function. We're going to identify where a function actually has no derivative at, and then we're going to learn all the basic derivative rules. And this piece right here is going to make what we did last week extremely easy, because now you're going to have rules you'll be able to rely on and do things a lot quicker, and it's just there's not a lot of algebra in it. Okay, so let's get started and jump into this. So let's talk about what differentiation actually means. So when you hear the term differentiation, that means that's the process of finding the derivative of a function. So what that means is, if I'm looking for average rate of change, if I'm looking for slope, if I'm looking for velocity, if I'm looking for any of those things, I am differentiating because I am taking the derivative. And that's key when you're going through this process, okay? Now, a function is differentiable. Now, here comes the important piece here, because there's a couple of things that you need to be aware of. So a function is differentiable at x if its derivative exists. So we have to have, first off, the derivative has to exist at x, and it's differentiable on an open interval as long as it's differentiable at every point in the interval. So what that means is that if I have a function and I'm focusing on a specific interval in that function, as long as every single point in that interval has a derivative, you're good to go. But if there's a moment where something is undefined within that specific interval, then it no longer exists. You can no longer find the derivative at that specific interval, because you do not exist somewhere along the line. So we talked about this earlier. The derivative of a function f prime of a function is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. This is talking about what we did last week. This is your difference quotient. Mind you, if you plug in 0 as it's written right now, you would get 0 over 0, because there's things that you have to do. So, when you're doing this, make sure that, you're going through the process, you are eliminating things and everything else. And then remember that sometimes when you go through this, your limit may not exist. So keep that in mind as well, okay? And we're going to talk about some of those today. These are the different ways that you're going to see the notation. So far, I've introduced you to this one, and this one, and this one, and this one. These two I have not introduced you yet, just because we just haven't got to it yet. So these are multiple ways. So when you see these things, you know you are differentiating, okay? And usually, typically the ones that are already highlighted, primarily this one, and let's see, this one's a big one. Those two you'll see the most often, along with this one. These two here are not as common. My dog is over here yelling at me because she wants to go outside. So sorry if you hear her in the background. But these two are not as common, but they are symbol notations for being the derivative. Okay. We talked about this one. So this is a different way, a different approach for the difference quotient. Instead of going through that whole long process, you can actually just do it this way at that specific value. And remember, I told you, if you do it this way, this piece here is going to cancel. So you're going to be able to factor this numerator up here, and it should cancel out with that denominator. Okay? Okay, so we're going to find the derivative here by the limit process. So what that means is we're going to do this. We're going to go the limit as h approaches 0. And that's going to be of f of x plus h minus f of x all over h. So this is what it wants us to do. Okay, so when we are doing this, make sure you keep everything in order. So as I'm going through this, I'm going to focus on this numerator piece first. So my f of x plus h, that's going to yield me x plus h cubed plus 2x plus h. Now, there's a trick for this piece right here. So I'm going to go to a different slide here. I'm going to show you this trick. It is called Pascal's triangle. And how you generate it, it looks like this. So you start with 1, 1, and 1. And then all your 1s are going to be on the outside. So 1, add those 2 together. That gives me a 2. And then nothing else to do, so there's a 1. So I'm going to go to my next line. 1, add those 2 together. Add these 2 together. And then that 1 follows down. And then I'm going to go to the next line. Start with a 1. Add those 2. Add these 2. Add those 2. And then drop my 1. I'll do one more just to show you the difference so that you can see. 1, 5, 10, 10, 5, and 1. So what this means is this. If I have, let's say, x plus 1 to the 4th power, and I want to expand this out, if I'm in this format here, the really nice thing about this is actually I have everything I need right here on this 4th line. So these numbers here tell you what power you are looking at, okay? So if I'm at the 4th power and I'm trying to expand this out, I'm actually going to come here to the 4th line, and I'm literally going to walk this down. So when I'm looking at this, I'm going to start here. This is to the 4th power, 3rd power, 2nd power, 1st power, and then no power. So when I expand this, this becomes x to the 4th plus 4x to the 3rd plus 6x squared plus 4x plus 1. Okay? There, done. I've already expanded it. I didn't have to go through a whole bunch of different processes. So this is called Pascal's triangle. So if you want to look it up and learn more about it, this does a whole lot of information for you for binomial theorem. So especially when it comes to expanding and everything. So that means when I come over here, here's a nice thing about this one. So when I come over here to this, and I want to expand this out, I'm going to start off with x cubed, and then it's plus 3x squared, and then I bring in an h. Then it's plus 3x. Now my h picks up 1, and then I'm going to end with an h cubed. So it's just a kind of a neat little trick or whatever that you can go through when you're expanding these, and you don't have to spend forever to actually be able to do these. And then I'm going to finish that out. Alright, I'm looking through here. I don't see anything to combine. So then I say f of x plus h minus f of x. So I have an x cubed plus 3x squared h plus 3xh squared plus h cubed plus 2x plus 2h minus x cubed minus 2x. And then I'm going to go ahead and divide everything by my h. So I'm going to do this in one step here. Okay, so we know that and that cancels, that and that one cancels. And I'm going to go ahead and divide each one by an h. So that gives me 3x squared plus 3xh plus h squared plus 2. So my limit as h approaches 0 of f of x plus h minus f of x all over h. That's going to wind up being 3x squared plus 2. And there you go. There is your answer. Okay? So just keep that in mind as you're going through. Keep everything in order or whatever else. And then, when you get down to this piece, now you can answer your questions off of whatever it's asking you to do. Okay? Oh, just talked about that. So use a derivative to find the slope at a point. All right. So we're doing a slope at a point. So now, if I didn't show you this before, I'm going to show you this now. I don't want to go through that whole entire process. Okay. What I want to do is I want to use my calculator for this one because this one's not going to be very nice and very pretty. So this is how we do this. We're going to go into our calculator. There it is. I know mine looks a little different than yours. Okay. And I'm going to come over here to my y equals, and I'm going to put in the square root of x. And then I'm going to hit graph. And then it's going to graph it. Now, it says I want to find the slope at the point 0, 0. So I'm going to go second trace and look here at number 6. And I want to focus in actually at 0. And I hit enter. This says non-real answer. Okay. Now, why would this be a non-real answer? Well, here's the deal. So let's take a look at this. If I come over here and I hit trace and I go to 0, I get 0, right? So I have a 0, 0, whatever else. So let's actually do the short version so I can show you exactly what's happening here. So we have the f of x minus f of c all over the x minus c. So when I plug everything in, I get the square root of x all over x. So the problem is here, I can't cancel anything. There's nothing I can do with this. Because remember, this is a 0 and that's a 0, so these pieces go away, leaving me with just this. So actually, at 0, 0, I don't have a derivative there. And I can look at that and see this as my reason why, because if I plug in 0, I get the square root of 0, which is a fine answer. You can actually have the square root of 0, but then it's all over 0, and I can't have that. So there's actually the derivative, so your dx does not exist at x equals 0. Now, with my handy dandy calculator, I don't know why I have to do this every single time. But with my handy dandy calculator, I can come over here and say the square root of x. So let's put this back in and hit my graph button. Now, but if I pick a different point, so let's say I pick 2, okay? I actually get an answer there. So you actually will get answers at any other point except 0, 0. So that's what it was kind of talking about there. And noticing that you're not able to actually go through that, okay? So that's just one of these things that you need to start being aware of, is that, last week everything existed. Now going forward, there's going to be some times where it's not going to exist at a specific point, and that's okay. And this is one of those ways here. Now your calculator, again, will help you with this. And I know you're not going to always have it, but when you do have it, use it and, take advantage of that so you can see what's going on. Okay? So find the derivative with respect to t for the function y equals 2 over t. So we're just going to find this derivative. Let's go through this real quick. So I've got So now let's talk about graphing. So I want to find f prime if f of x equals x cubed minus 1. So then the graph of f of x and x prime, then I want to graph those x primes on here, okay? So what I want to do is I want to come over here and I want to graph my x cubed minus 1. So, I don't have that on here. Oh, I do. So when I do that, I get that, okay? So this is the x cubed minus 1. So now I want to go through here and I want to graph it on the same coordinates, on the same set of axes. So I'm going to have to use that difference quotient because I can't do the f of c because I don't know what my c is, okay? So what I want to do is, again, go through your process. So I'm going to come over here, I'm going to go here, and I'm going to say the x plus h, so f of x plus h minus f of x all over h. So that's going to generate x plus h cubed minus 1 minus x cubed plus 1 all over h. So then that will generate x cubed plus 3x squared h plus 3xh squared plus h cubed minus 1 minus x cubed plus 1 all over h. So that and that and that and that. So I am left with 3x squared plus 3xh plus h squared. And when I run that limit to 0, I wind up with a simple 3x squared. Okay? So what I do there is now I just graph it. So I know that, let's find a creative one here to actually do. So I know when x is 0, y is 0. There's my first one. I missed that one. Let's try it again. There you go. When I plug in a 1, I get a 3. And then negative 1 because it's a parabola, so we're going to be uniform across the board. And then notice the next one's going to be at 12, so I'm going to be up here somewhere, so I'm off the board on both. So then I'm just going to kind of connect the dots. See if I can do this. So there's that. Oops, that was really bad. So I'm going to do it again. Okay, so there we go. There is our graph. The red is the f of x, and then the blue is going to be our f prime of x. So notice that a cubic turns into a squared, a parabola. Okay? That's it. That's all it's asking you to do. And we're going to find out more later what this actually means here. Okay? So now, let's talk about identify where a function has no derivative. So there are 3 ways that a function has not, that a function has no derivative. I'm sorry, that is a really bad typo there. So let's fix that real quick because that would just irritate me. There we go. Much better. So number 1, the function has a limit to the left and the right, but the limits are not equal to each other. This happens when there is a corner. So if we take a look at this, we call this a corner. So notice how we have this very sharp point right here at 0, 0. Now that makes sense if you think about this, because what type of a graph is this? Well, if you know this correctly, this is the graph of an absolute value. And so if you notice that I'm coming down, and then I get to 0, 0, and then I am turning and going forward. So when I'm doing this piece here, I have this very sharp turn right here, and you can't have that. When you're looking for a limit, when you're looking for the derivative, you have to be continuous. It has to be a smooth curve. Well, this is continuous, but this is not a smooth curve. This is a point, and you can't have a point. It's basically two lines meeting at one point is what this is saying. The next one is the one-sided limits are both infinite and both equal either positive or negative infinity. When this happens, the graph has a vertical tangent. So this is the cubic graph. So this one would be f of x is equal to the cube root of x. So this is what this one looks like here. So when I'm looking at this, I've got this cube root happening. And so basically something happens like right here in this spot here. You notice it's kind of almost vertical straight up and down. So that means like right here, I do not actually have a derivative at this specific point. Now, I have derivatives out here. I have derivatives out here, but right here, the function as a whole does not have an actual derivative as a whole, because I actually have issues that are happening right here. We're vertical. And then we have what's called the cusp. So both one-sided limits are infinite, but one equals negative infinity and the other equals positive infinity. When this happens, the graph has a vertical tangent line at the point, and the point is referred to as a cusp. So we're looking at this point right here. So notice how we're coming into this direction, and then we're leaving going into that direction. If you take a notice here, this looks like the square root of x going out to this direction here. And then this looks like maybe the negative version over here. So you have both of them, the plus minus, looking at them together. But notice when they meet up here, we have this really, it's again, yes, we're continuous, but now we're down here to this point, and it's kind of pointy right here, and you can't have a point. Remember, when we're talking about derivatives, you've got to have nice, pretty little curves. Notice there's none of this stuff happening here. There's none of this stuff, but what both of these have in common is that point right there, and you cannot have that point when you do this these derivatives. Okay, so we are given this, and we are going to be determining if f prime of 1 actually exists here. Okay, so what we're going to do is we're going to see if, when we go through this process, if the derivative focusing at 1 is actually going to exist or not. Okay? So, what do we do here? What do you think the first option is? Well, we need to see if we're going to be continuous. That's our very first thing we're going to do, because if we're not continuous, this isn't going to work. So, you come over here and you say, all right, well, let's go negative 2 times 1 squared plus 4. That gives me negative 2 times 1 plus 4. So that gives me a 2. Okay. Then I say 1 squared plus 1. That gives me a 1 plus 1. That gives me a 2. So I am continuous. That's a good thing, because I need to be continuous. So now what we need to do is now we need to check their limits. So the easiest way to do this, since they went ahead and gave us points here, what we're going to do is we're going to use the f of x minus f of c all over x minus c. Okay? We're going to use our limits here, and we're going to see, okay, well, if this is really the case and it's really continuous, well, let's focus on and see what happens when we actually do this at this point to see if our limits are actually going to be the same thing. So we're going to start off with the limit as x approaches 1 from this side, from the left side, which means I'm going to be focusing on the negative 2x squared plus 4 piece. Okay? So we're going to run that one first, and then we're going to look at the limit as x approaches 1 from the right side of the x squared plus 1. So we're going to be looking at both of these to see if these limits match. Because if the limits match, we already know it's continuous. So that's a good thing. So we're good to go there. Now the next thing to know, if we actually have a derivative here, is now both of these limits have to match. So we have negative 2x squared plus 4. And then we have minus that c value that we did, so minus 2, all over x minus 2. No, sorry, not 2. 1. This gives me negative 2x squared plus 2 all over x minus 1. So then I'm going to clean up this. So I'm going to pull out a negative 2. And that gives me x squared minus 1 all over x minus 1. So then negative 2, x plus 1, x minus 1, all over x minus 1. Those cancel. So then I've got negative 2 of x plus 1. I'm going to run that at the x is equal to 1. So I get negative 2 times 1 plus 1, which is negative 4. So this is my first one. So in order for this to be differentiable at this specific point, when I run the limit over here of the other one, we have to get a negative 4 as an answer. So then, here we go. We have x squared plus 1, then minus the 2, all over x minus 1. So we have x squared minus 1, all over x minus 1. That gives us x plus 1, x minus 1, all over x minus 1. Those cancel, leaving me the x plus 1. And we want to run this at the x is equal to 1. And so when we do that, we get the, jumped ahead. We get 1 plus 1, which is 2. So since these two do not exist, or I'm sorry, not do not exist, since these two are not the same thing, then the answer is no, there is not a derivative at x equals 1. So since the one-sided limits are not equal, then the derivative does not exist. So you can say it a couple of different ways. We're saying that this one and this one, since the one-sided limits are not equal, and we prove that right here, since they're not equal, then you can say f prime of 1 does not exist. So just, however you want to write it, make sure that you give a kind of a complete picture. When you're writing your free response questions, so since the one-sided limits, that they exist, but they're not equal, are not equal, then f prime of 1 does not exist. So this should actually be your true and final answer right there. That is what, when you write a free response question, that is what they're looking for, and that's what you need to do. Okay? You explained why you're saying it does not exist. You're saying because the one-sided limits are not equal, they don't exist. Okay? All right. We need to show that x minus 2 to the 4/5 has no derivative at 2. So again, we're going to do the same exact thing. So when I go through this process, I'm going to use the f of x minus f of c because they actually, it was minus c, not x again, because they actually gave us a point here, all over x minus c. So I'm going to look at both the left and the right. So the limit as x approaches 2 from the left, that's going to give me the f of x minus f of c all over the x minus c. I'm going to start with this one first. That gives me x minus 2 to the 4/5 minus 0 all over x minus 2. And don't forget, you get the 0 when you plug in the x value to get that y value. 2 minus 2 to the 4/5 is 0. That's where that 0 came from. So then I have x minus 2 to the 4/5 all over x minus 2. Okay, so here you need to remember your power rules. Because right now, this is an ugly problem. However, because I have power rules that tells me I can move things around, if I take a look at this, what I'm really looking at down here is x minus 2 to the 5 over 5. Because it's to the first power. First power is 5 over 5. And so then if you remember, you've got an exponential rule that says if you have m to the n over x to the y, and if I move things around, I can really say this is 1 over, oops, not m. Oh, let's try this again. I used the wrong letters. I have m to the n over m to the y. There we go. That's what I was looking for. That means I have 1 over m to the y minus n, because I can move this around because my bases are the same. Over here, I have bases are the same, so that means I can move this down. So when I do this, I'm going to move this 4/5 down here and subtract it from that 5/5, and then I wind up with 1 over x minus 2 to the 1/5. Now, when I put that 2 in here and I run that limit as x approaches 2, I wind up with a 1 over 0. And since I'm coming from the left-hand side, that means that if I keep putting in negative numbers over here, -3, -4, -5, so on and so forth, I'm actually coming from negative infinity. Okay? So same thing on the other side. The limit as x approaches 2 from the positive side of f of x plus f of c all over x minus c. So that's going to generate the x minus 2 to the 4/5, again at that 0, all over the x minus 2. Okay, so it's going to be the same thing as what we have over here. So if that's really the case and I plug in that, I'm going to get a 1 over 0. So when I get down to this piece right here, I get x minus 2 to the 1/5. And when I run it to 2, I get 1 over 0. And now to know if it's positive or negative infinity, I pick a bunch of positive numbers. So 3, 4, 5, 6. And if you notice all those are positive, it'll generate a positive. That means I'm coming from positive infinity here. So what that means, now that we've done this, we wound up with a negative infinity and a positive infinity. What that means is the graph has a vertical tangent line at x equals 2, which is a cusp. So, and therefore, f prime of 2 does not exist. Okay. So, when you do this, I'm going to go back a few slides. We're on 19, so I just remember. So, when we do this, and we're talking about this, this is what this one's talking about here. So, one is positive infinity, and the other one's negative infinity. So, when it happened, we have a graph that's going to do something like that. Okay, so when we're looking at the graph, we have this happening here, and so since we know this is happening, we have a cusp here, and so that we know that there's not going to be a derivative there, and so therefore that derivative is not going to exist. And if you need to take a look at it just to prove so that you can see what it looks like, again, you have a handy dandy calculator. So then we come in here and we go through this process every single time because I don't know why. So then we have x minus 2 raised to the 4 over 5. And you can see there's that first one there and there's that second one. So you can see that cusp happening right there. Okay. So that's what it's talking about, that you're coming in, yes, you're continuous, yes, everything is fine, but when you get here, something weird happens. We have that cusp that happens, and so therefore you do not exist at that 2 value. All right. Okay. So let's talk about differentiability and continuity. This is kind of a short and sweet, so this is kind of nice. All right. So what we're going to do here is just going to look a little bit. We're going to talk about continuity and stuff. So remember what we did earlier when we were talking about limits and everything. We also talked about continuity of a function. Today we were talking about differentiability of a function, and then there's this connection that exists between differentiability and continuity. So the first one is if a function f has a derivative at the number c, then f is continuous at c. So this is saying if I have a graph, something that looks like this, doesn't matter, and I'm focusing here at c, so this is saying I actually have a derivative at this number here because I'm continuous, because it's saying that I'm continuous here at c. So if I actually go through this process and find out that yes, I actually have a derivative, I can tell you what it is, then I am continuous. If a function of f is discontinuous at the number c, then there is no derivative at c. So again, if I've got, oops, not that, I'm not sure what that was. So if I've got something that looks like that, and this is my c value here, I'm not continuous. And so when I'm actually looking at c, then I'm not going to have a derivative here because there's no c value there. So that's what it's saying there, okay? Which means differentiability implies continuity. So if you're differentiable, then you have continuity. However, The reverse of this is not true, and be careful of that. Continuity does not imply differentiability. And here's two examples of what I'm talking about here. If I run a limit on one here from the left side, I can actually get an answer, but I won't get it from this side here. And my two limits are not the same. So I'm continuous from the left side here, but if I look at one as a whole, I'm not continuous all the way through. So that's the first piece. But this piece here is where it actually all goes down here, hill. I am continuous all the way through this specific graph right here. I have a limit. However, my limits are going to be a little bit different here. But this piece right here, this is why this is not differentiable. Differentiability happens on smooth curves, things like this. It does not happen there at those points in cusp right there. So that is why continuity does not imply. Please make sure you understand this. This is one of the biggest pieces of derivatives. Continuity does not imply differentiability. But if you can find and take the derivative of that specific point, then yes, you are continuous. Okay? All right. Now, on to the fun stuff. Because now your life is about to get a little bit simpler. We're going to look at basic derivative rules. So there's several differentiation rules that you are going to have to commit to memory. And so, and you'll get charts and stuff to help you remember all this. So, write this down somewhere, but you're going to have to start committing these rules to memory. The good thing is we'll use this so many times that you're just going to know it. So it might take a while in the beginning, but eventually you're just going to know exactly what these rules are. So let's start off with the constant rule. So if I have a constant, y equals 3, y equals 15, y equals 4,722, when I take that derivative, the answer for that derivative is always going to be 0. Oops, that is not a highlighter. So if you have a constant, its derivative is 0. So that looks like if I have f of x is equal to 7, when I take that derivative, I'm going to get 0. That's because if I was to graph this at 7, I go straight across just like that. That's y equals 7. It's a horizontal line, and a horizontal line has the slope of 0 because remember, derivative is slope. And so we're looking at the slope of the actual function. That's why the derivative of a constant is 0. Power rule. This is probably the most widely used and most important rule of them all. If you have a function, the derivative is you're going to bring down the power and multiply it to any coefficient you have in the front and subtract 1 power. So this is what your difference quotient has been doing for you. Okay? So what it's been doing, it's been saying, okay, so the difference quotient actually gives you this piece right here. So now you have this huge, powerful tool here. Now you don't have to use a difference quotient no more unless the rules say to. So yay on that. You just come over here and use this. So if I'm looking at this and I want to find the derivative of 6x to the 4th, if I follow this, I'm going to say 4 times 6 is 24. Leave my x there. 4 minus 1 is 3. That's it. You're done. Nothing else to do. No long mathematical process or anything else. Please don't throw things at me. This is what this is the power rule. This is probably the most widely used rule that you're actually going to wind up doing. Okay? Same thing over here. G prime of y. Watch this. I can do this in 10 seconds. 5 times 9 is 45. Y to the 4th. Ooh, that was fun, huh? Now, on this one here, I would not run the power rule as is, because this is actually not in a power rule situation. So when you're looking at and trying to use this, you want to make sure that you don't have any fractions like this. So the first thing I'm going to do on this one is I'm going to rewrite this, and I'm going to move everything up, and I'm going to split stuff up. So instead of having 1 over 3 t to the 7th, I've actually got 1/3 t to the negative 7th. Because remember that this right here is 1/3 times 1 over t to the 7th. So all I did was break this up so you can look at it like this. Because now, when I actually run this piece through here, and I want to find the prime, I'm going to go negative 7 times 1/3. That gets me negative 7/3. And I'm going to subtract the 1 from it. So that gives me t to the negative 8. And I can leave it like that, or I can turn around and put it in a different format. If it wants it where exponents are positive, because you will see that as an actual direction with positive exponents, you just go negative 7 over 3t to the 8. Okay? They mean the same thing. All right. Sum and difference rule. And so this is saying, all right, if you have the sum and difference rule, you're literally going to take the derivative of each term in here. So those huge long polynomials that we've been doing, basically what you're going to do is you're going to take the derivative of each individual term that is in that polynomial. So if I'm looking at this over here, I'm going to take the derivative of this first, followed by the derivative of that second. Well, when I'm looking at this, and I take the derivative of 3x squared, that gives me 6x. When I take the derivative of 8, well, the derivative of a constant is 0. So therefore, when I take the derivative of the whole entire thing, it's just 6x. Because you got to remember, you're taking the derivative. So you're finding f prime of, let's change it so you don't get that mixed up. We're going to say g of x is equal to 3x squared. And we're going to say h of x is equal to 8. And so if I go g prime of x, that's your 6x. And if I go h prime of x, that's your 0. When you combine those together, you get this piece right here. So that's all it's saying when you're talking about sum and difference rule. You're going to look at the specific term, and then you're just going to take the derivative of that specific term and then add or subtract them together. Okay? E to the x. This is probably the most simplest one to remember, because if you have y equals e to the x, then y prime is e to the x. It is what it is. There's nothing that you have to worry about doing. It's just, it is what it is. Okay? Then we have the derivative of sine and cosine. So this is actually a pattern. We'll learn this when we do multiple derivatives later, that there's actually going to be a pattern to this. But the derivative of cosine is negative sine, and the derivative of sine is cosine. All right. So cosine is negative sine, sine's prime is cosine. To keep those two in mind somewhere. Let's look at some examples here. Find the derivative of f of x is equal to 2x to the 4th minus 6x squared plus 2x minus 3. You should be able to do this problem in about 15 seconds at this point now. So we say f of x equals, or f prime of x equals 8x to the 3rd minus 12x plus 2. And you are done. Okay? It's just the power rule. Power rule, power rule, power rule, power constant rule in this one. So just remember that. What is f prime of 2 if I give you this? So we just did this. So again, this is 8x cubed minus 12x plus 2. So we want to know what is f prime of 2. So f prime of 2 is 8 times 2 cubed minus 12 times 2 plus 2. So this is 8 times 8 minus 24 minus 2. So this becomes 64. I'm sorry, not minus, just plus 2. Sorry. Minus 22. So that gives me 42 as my answer. All right. So we want to find the slope and the equation of the tangent line to the graph of f at the point 1, -5 using that same formula. All right. So we are using the same formula. So I'm going to say f prime of 1. That gives me 8 times 1 cubed minus 12 times 1 plus 2. And that gives me a -2. So that's what it's asking on this one. So we found the slope. Now we're going to find the equation of the tangent line. So y plus 5 is equal to -2 times x minus 1. Now, did it tell me to put this in y equals form? No, it did not. So technically you would stop here. But if you are one of those people who absolutely needs to have it into y equals mx plus b form, go right ahead. Just be careful. Make sure you are not making any mistakes. Make sure you are following through with your signs and everything else. Okay? So on our free response question, if it doesn't tell you which one to do, either one works. My personal opinion, I would stop here. But if you have to do some graphing, obviously you're going to have to take it a little further down. Okay. Now let's look at the normal line. So we know that the slope at 1, if I remember correctly, was -2. So that means the slope of the normal line, so f1n of 1, that's going to be flip, change of sign. It's 1/2. So then this is y plus 5 is equal to 1/2 of x minus 1. And leave it alone. Because I did not tell you to put it in a y equals form. Okay? All right. Find the points on the graph of where f of x equals 4x cubed minus 12x squared plus 2, where f has a horizontal tangent line. So what this means is I need to take my f of x, or my f prime of x, and I need to set this equal to 0 and solve. So that's what I'm going to do here. So the first thing I'm going to do is I'm going to find my prime. So this gives me 12x squared minus 12x. I'm going to clean this up. So that's 12x times x minus 1. Is that right? Oh, yeah. And then I'm going to set this equal to 0. Okay? So then I'm going to say 12x is equal to 0. And I'm going to say x minus 1 is equal to 0. Oh, wait, did I make a mistake? I made a mistake. Hold on. All right, so now we're going to find the points of the graph where f of x equals 4x cubed minus 12x squared plus 2, where f has a horizontal tangent line. So what I'm looking for here is I'm looking for when my prime is equal to 0. So the first thing I need to do is go ahead and take this derivative. So when I do that, I get 12x squared minus 24x. And then I'm going to go ahead and factor this out. So 12x, that leaves me with an x minus 2. So then I'm going to set each piece over here equal to 0. 12x is equal to 0, so that means my x is equal to 0 for this one. I'm going to move that 2 over here. And so I get x equals 2. So I have horizontal tangent lines at x equals 0 and x equals 2. What does that mean? That's your turn points. So if you want to go ahead and jot this down, we're going to learn about this later on. But whenever your f prime of x is equal to 0, these are your turn points. So you're getting kind of an inside look of what we're going to be doing later on. So anytime it asks you to find the horizontal tangent lines, it's asking you to find turn points. So just to keep that in mind, okay? So where is f prime of x greater than 0 and where is f prime of x less than 0? So what we're going to do here is we're going to do sign charts. So remember we talked about sign charts a while back. So what we're going to do is we're going to draw a sign chart. Okay. And I have a 0 and I have a 2. So I have a 0 and I have a 2. And what I want is I want to pick numbers less than 0. So I'm going to pick a -1. In between 0 and 2. So I'm going to pick a 1. And then greater than 2. So I'll pick 3. Your choice. You can pick what you want. Okay. Change these colors up here because I don't want you to get them mixed up with the zeros here. Alright. That's fine. So now, what we're going to do is we're literally going to go back into our prime. So we're going to rewrite my prime here. That f prime of x is equal to, what is it, 12x, and then x minus 2. So then I'm going to evaluate this piece here at these 3 numbers. So I'm going to come over here and I'm going to say, on the first one, at -1, I'm going to say 12 times -1, and then -1 times -2. I get -12 times -3, and negative and a negative is a positive. And then I'm going to do the same thing with the 0, or well, in between anyway. So I got 12 times 1, and then 1 minus 2. 12 times a -1, a positive and a negative gives me a negative. And then I'm going to do the 3. So I get 12 times 3. 3 minus 2. So I get 36 times a 1. So I get a positive. So notice I didn't care about the actual numbers themselves. All I cared about was the sign. All I care about was the sign. So now I can go back up here now that I've done a sign chart. And now I can tell you exactly what's happening here. So where is f prime of 0 greater than x? Well, it's greater than x from -infinity all the way to 0. And I'm going to union that to infinity. So that's the first piece. I am less than 0 from 0 to 2. Okay. So when it's asking where are you greater than or less than, you're going to need to make a sign chart. And you're going to need to be able to plug numbers in that are less than your zeros, or greater than your zeros, or in between your zeros. And then you're just going to look at the sign. We don't care about the numbers. We only care about the sign. Okay? Only care about the sign. Next problem. Find f of x when f of x equals 4e to the x plus x cubed. Okay? So, when I'm doing this, again, we're going to look at this one first, followed by this one. All right. So, if I have my g of x is equal to 4e to the x, since this is just being multiplied here, I don't actually have to do anything with that because that's an actual number and it's not a variable. I leave that alone. So when I find g prime of x, that 4 is just going to sit there, and then e to the x, when you take that derivative, is simply e to the x. My h of x is x cubed. So that means h prime of x is 3x squared. So when I'm looking for f prime of x and I put everything back together, that is 4e to the x plus 3x squared. All right. More examples. So problems 1 through 3. Find the derivative of the function. Find the points where the graph of each function has a horizontal tangent line. And examine the graph to determine if your answers are reasonable. So first thing I want to do here is I want to find the prime to this. So I've got y prime is 3x squared minus 6x minus 9. I want to set this equal to 0. Nope, I wrote 3x. That's supposed to be 6x. And then I'm going to factor. Pull out a 3. And then I'm going to factor again. It's x minus 3, x plus 1. Set each of these pieces so that 3 doesn't count. So x minus 3 is equal to 0. X plus 1 is equal to 0. So that x is equal to 3. And x is equal to negative 1. And so if you take a look here, over here at the graph, my horizontal tangents are here at negative 1 and positive 3, which makes sense. Because I told you earlier that if you have, if we're looking for the zeros here, you're looking for turn points. And that's exactly what we have there. We have turn points at those specific things. Okay, give you a couple of seconds. Pause the video. Try number 2 on your own. And pause it now. All right, welcome back. Let's see how you did. Y prime gives you x to the third minus 4x. So y prime, pull out an x. That gives me x squared minus 4. So y prime is x minus 2, x plus 2. So when I'm looking at this, I have zeros at x is equal to 0, and then a 2, and then a negative 2. And if you look, I have turn points here, here, and there. So yes, that is correct. All right, one more. Again, pause the video now and do these problems. Okay, welcome back. So this becomes 2x cubed plus 3x squared minus 2x. So I'm going to pull out an x. That gives me 2x squared plus 3x minus 2. So I need factors of 4 that subtract to give me a 3. So my 3x, I'm going to rewrite my 3x as 4x minus 1x. So this is just factoring, is all I'm doing here. That's x, so 2x squared plus 4x minus x minus 2. So then my x sits there. So I'm going to have a 2x, and I'm pulling out here. That gives me an x plus 2. And I'm going to pull out a negative 1 back here. That gives me an x plus 2. Ooh, that's good to go. So I'm looking at x times 2x minus 1 and x plus 2. So that means I have zeros at x is equal to 0, 1/2, and negative 2. So there's my negative 2 There's my 0, and I know it's hard to see, but there's my 1/2. All right. So now, suppose that the functions f and g and their first derivatives have the following values at x equals -1 and x equals 0. Find the first derivative of the following combinations at the given value of x. So I'm looking here. I want to find those first derivatives. Okay. So on this one, at -1, I want 3 times f prime. So what I'm doing, I've got 3 times f prime of x minus g prime of x. So this is what this is asking us to do. So I have 3 times f prime. So that's this piece right here. 2 minus g prime, which is 1. So 6 minus 1 gives me 5. Okay. So pause the video, try B, C, and D, following the same steps as I did here, and using the chart and go through the process and see what you come up with. Pause it now. All right, welcome back. Let's see how you did. On this one, f prime of x minus e to the x. So f prime of x at 0 is -2. So I've got -2 minus e to the x. There's nothing else to do with that one. Actually, you know what? I could actually simplify that a little bit more. So let's take that back. I lied to you. Because we're looking at it actually at 0. So I've got -2 minus e to the 0. So that's -2 minus 1, which gives me -3. Because I'm actually looking at it at 0. So on this one, g prime of x plus 2 times f prime of x. And we're looking at it at -1. So g prime of x is 1 plus 2 times 2. So you should get 5 here. And then again at 0, so we have 4x cubed plus f prime of x minus 3g prime of x. And we're looking at 0. So at 0, this goes away. F prime gives me -2 minus 3 times 4. That's -2 minus -12. That gives me -14. Okay? All right. Last part. Now we're going to be looking at a graph here. So in the graph above, determine which points will correspond to the derivative f prime of x in which f prime of x is negative, f prime of x is positive, f prime of x is 0, and f prime of x has the largest absolute value. So when you're looking at a graph, okay, and you're looking at this big, huge graph here, this is what you need to remember. If I'm decreasing on a graph, I have a negative slope. If I'm increasing on a graph, I have a positive slope. And if I'm at a turn point, I have a 0 slope. So let's start with number 3 first and identify our turn points. Our turn points are B, C, and E. Okay, so we don't have to worry about those because those are now done. So I need to know here on number 1, where am I decreasing? Well, I'm decreasing at A, and I'm decreasing at F, and I'm decreasing at G. So those are done there. Number 2 wants to know where am I increasing at? I'm only increasing at D, which is right here. So when you're looking at a graph and we're talking about slopes, remember we're talking about slope. On the original graph, we're talking about where am I increasing, where am I decreasing, or where do I have turn points. So that's what we're going to kind of look at. The largest absolute value is the closer you are to actually the, I'm sorry, not the closer you are. The further you are away from, not further, I'm sorry. The closer you are to the actual x-axis here. So if I'm looking at this, the one that's actually closest to the x-axis is actually going to be A. So that's going to have the largest absolute value. Okay? All right. So, all right.